The dot product is a special operation. We've mentioned it. Takes two vectors in n space, does something to them, and then it outputs a single number, a scalar. What it does really is it finds a way, when you're given vectors, to talk about the length of the vector, but also about the angle between the two vectors. So the scalar product, the dot product, the inner product, is a way to extract information about the angle found between two vectors. If you're working in R2, that's easy to sort of do, right? If you have two angles, two vectors, this is your angle between them. If you're in R7, it's less obvious what an angle would be. And later on, when we expand the notion of vectors to things that are not arrows, we'll still be able to define an inner product, or at least very often we're able to do so, but we're not talking about arrows anymore. Like sometimes we'll be talking about matrices. Like we can think of matrices as vectors. What does it mean to have an angle between matrices? Oh, there's still something that could be defined. The dot product of two vectors, u and v, assuming the coordinates of u are x1, x2, x3, and of v of y1, y2, y3, it is fairly straightforward. You actually multiply the corresponding components. Once you have these products, you add them together. That's also the definition when you're in n space rather than 3 space. Right? So you look at all the corresponding coordinates, you multiply them together, you'll have n products, and then you add these n products together to get the inner product, the dot product. And I've mentioned it before, but I'm going to re-emphasize that here because it's important. This result, this operation gives you a scalar, right? The end result of this is a number, this is a number, this is a number. You add things together, you get a number. Later on, not in this course, but in more advanced courses, you'll see that it makes more sense to define these where the scalars are not the real numbers, but they're the complex numbers. But in our course, that's not going to be the case. In our course, the inner product, the dot product of vectors is always a real number. There are important quantities you can compute with this. The first one is the length of u. So when we are talking about a vector and we want its magnitude, we typically represent that with the double lines. When we were talking about a complex number or even a real number, we computed the absolute value or the modulus, depending on whether we're in R or C. Well, this is sort of a generalization of that. But when we're talking about vectors, we have the double line, right? So double line here really is specifying that we're looking at the length of a vector. And in R3, the length of a vector would be, well, what is it? It's the square root of the square, or the sum of the squares of each of the coordinates. But we know what this is, right? x1 squared plus x2 squared plus x3 squared. This would be exactly u dot u, right? If u and v were exactly the same, then y1 would be x1, y2 would be x2, y3 would be x3. So in this sum here, we would have x1, x1, x2, x2, x3, x3, x1 squared, x1 squared, x3 squared. So you can compute the length of u, length of the vector u, by first computing the inner product, the dot product of u with itself. That's a scalar number. It's going to be positive, or at least non-negative, because you're looking at squares here, and you take the square root of that. Another quantity that you might be interested in is the norm. And this is what we call these double bars here, magnitude or norm. The norm of u minus v. That actually measures something. It measures the distance between u and v as vectors. Looking at this quantity here. There's a nicer drawing of the situation. This is the vector u, and this is the vector v. U minus v would be the vector between the tips of u and v pointing towards u. You can visualize this if you wanted to know for how do I know that the length of u is indeed this like, you know, x1 squared plus x2 squared plus x3 squared, and take the square root of that. You can visualize that by looking at the cube, where one corner of the cube is the origin and the opposite corner is the point of the vector, and then you just do repeated applications of Pythagoras' theorem to get the formula for the length of u. These definitions apply not just to R3, they apply in general to n space. The only difference is that you might have more than 3 sums here, 3 terms to add together. The norm, the magnitude of u, then would just be the square root of the inner product of u with itself. It's this quantity here. So there's 2 formulas here that are important for you to remember. U dot v is this thing, and the length of u, the magnitude of u, the norm of u is this thing. When you equip Rn, n space, with the dot product defined here, you actually give Rn a new name. We call it Euclidean n space. And you heard me slip earlier and I called Rn Euclidean space. It's because I was sort of like cheating a little bit and telling you or letting you know that we were going to be dealing with Rn not just as a space of vectors, but a space in which we have an inner product, a dot product. And once we have an inner product, a bunch of nice things can actually happen. This is something that some of you will study in the 2nd year and 3rd year linear algebra course. Well, let's do a few examples. So you have 2 vectors here. What space do they live in? It's not explicit, it hasn't been written down, but we see u has 1, 2, 3, 5 components, so does v. So both of these vectors, u and v, actually live in R5. We know that R5, when we equip it with the inner product, the dot product is a Euclidean space. We can compute the inner product of u and v. We just do pairwise products of each of the components. So 1 times 1, 2 times 3, minus 1 times 2, 0 times 1, 1 times 1. So that gives me 1, 6, minus 2, 0, and 1. And I add them all up together and I get 6. That's the numerical value. Now, u dot v could be 0, could be negative. U dot u cannot be negative. That's impossible. And if you wanted to, say, compute the norm of v, the length of the vector v, all you would have to do would be to take the square root of the square, or the sum of the squares of each of the components in v. So 1 plus 9 plus 4 plus 1 plus 1 gives me 16. Square root of 16 is 4. Remember, when we take the square root by convention in this class, we're talking about the positive one. And so the length of v is 4. Obviously, the length of a vector has to be greater than or equal to 0. The length of any vector has to be has to be non-negative. It could be 0 though. But the only way for the length of a vector to be 0 is if the vector is 0 to start with. That's the only vector that has a length of 0. Any other vector than the 0 vector has a length greater than 0. So if the length of a vector is equal to 0, that means the square root of the sum of the squares of each of the coordinates is 0. So I can square both sides of this equation, and I have the sum of the squares of each of the coordinates is 0. Each of these quantities, the ui squared, they're all non-negative because it's the square of a real number. So everything has to be greater than or equal to 0. But if this thing is equal to 0, if the sum of them is equal to 0, what it means is that the square of each of the coordinates separately has to be equal to 0, which means that each of them separately is equal to 0. The square is 0, the actual value itself is 0, which means that that vector is 0. Feels a bit like overkill to have to do a proof like this, but I've told you that if the length of a vector is 0, it has to be the 0 vector, but I just told you, how do you know that I'm not just making things up? So there's a balance to be found between being skeptical and being too fastidious, right? There comes a point where you're going to have to take certain things on faith. Worst case scenario, you can prove the thing you took on faith later. You can say, let's assume it's true for now and see where we go from there. That's what we do in mathematics very often. Like, if this was true, this is what would happen. Afterwards, we can work on trying to demonstrate that this set of basic stuff is true. And we also have the property that the inner product is commutative. And this sort of distributivity of vector sums with respect to the inner product, right? These two properties are more or less what you would expect to hold, and we're lucky that it does. Didn't have to, but it does.